Last week, we learned about ways to come up with estimators for parameters. We talked about an important way to do that. That's the sample analog principle. And we have also learned how to evaluate the accuracy of the estimators. We talked about one way to do that, that is by Monte Carlo simulations. Monte Carlo simulations is a direct way to evaluate the accuracy of estimator because using Monte Carlo simulations, we can directly calculate the bias, variance, and mean squared errors of estimators. However, Monte Carlo simulation has its limitations. A very important limitation is that in order to do Monte Carlo simulation, you have to specify from which distribution your data is generated from. You have to specify the data distribution under which you are. Last week, we learned about ways to come up with estimators for parameters. An important way to do that is by sample analog principle. The sample analog principle is a general principle to motivate parameters, but sometimes it motivates more than one parameters. Then there is the need to evaluate the accuracy of estimators and to compare them. Even when you are not comparing different estimators, sometimes it's useful to know how accurate your estimator is, how different it is from the true value. We learned one way to evaluate the accuracy of the parameter of the estimator, and that is by Monte Carlo simulations. Monte Carlo simulations is a direct way to evaluate how an estimator performs. It directly calculates the bias, variance, and mean squared errors. However, Monte Carlo simulation has its limitation. A very important limitation is that you have to specify the distribution from which the data is generated in order to compare estimators, in order to calculate the bias, variance, and mean squared errors of the estimator. Often, it is not very clear what distribution you want to specify. Sometimes you might know that you want to evaluate the estimator performance of the estimator under a Poisson distribution, for example. But even then, you don't know what lambda you want to use to generate the data. In general, it would be good if estimators, if relative performance of estimators do not depend on the distribution you generate the data from. But that is not always the case. Sometimes the relative performance of estimators do depend on from which distribution you generate the data. So it is not an ideal tool to use. So Monte Carlo simulation is not an ideal tool to use when you want to evaluate the performance of the estimator in more general sense. Today, we will talk about some analytical ways to evaluate the performance of estimators. Let's focus on the simple case where our parameter of interest is the population expectation, mu, and our estimator is the sample average from an IID sample. One simple measure of accuracy is the variance of the estimator. The variance of the estimator in the case of estimating the population expectation using sample mean is easy to calculate. So the variance of the sample mean is easy to calculate. Variance of the sample mean is variance of 1 over n times the sum of all the observations in the data. So the data set that we use, if I don't specify, then it is an IID sample. So all the xi's are independent from each other, and all the xi's also have the same distribution as the population distribution as x, which is our variable of interest. Okay, so the variance of x in bar, variance of the sample average, is the variance of this, which is just another form to write the sample average. Invariance of a constant times a random variable equals square of the constant times the variance of the random variable. So that's a property that variance has. And now we want to know what is the variance of the sum of these n random variables. Variance of the sum of random variables in general is not equal to sum of the variances of the random variables. But we have the extra condition that the random variables are independent from each other. When these random variables are independent from each other, the variance of their sum equals the sum of their variances. So therefore, the following equality hold. This variance equals the sum of the variances of each of the random variables in the sample. So this is by independence. And now we're going to use the identical part of the IID assumption. Identical means that all the xi's have the same distribution. And because they are all IID sample of x, they all have the same distribution as the generic x. Okay, so they all have the same distribution, all of them equal variance of x. Therefore, these n copies of them add up to n times variance of x. And n times variance of x times 1 over n squared becomes variance of x divided by n. So therefore, that's sigma squared divided by n, where sigma squared is the variance of x. So here this mu is the expected value of x, where the variance of x is sigma squared. Okay, so I already have that. I just wrote it again. So that's contains the same information as this part. Okay, so therefore, variance of sample average equals sigma squared divided by n. What we can see from here is that the sample average, the variance of the sample average decreases with the sample size. It has an inverse relationship with the sample size. But we still do not know what this exactly is because we do not know sigma squared. So sigma squared is in general not known. So knowing this formula doesn't help us that much regarding the accuracy of the sample average as an estimator for the population expectation. Fortunately, we are able to estimate sigma squared. So we have actually talked about the estimation of sigma squared in previous lectures. We know we can estimate sigma squared using the following estimators. So we talked about two kinds of estimators. One estimator is this direct sample analog of the population variance. So that's this one. And we have shown that this is consistent. And there is another one that is slightly different, but really not that much. This one is also consistent. So we have at least two consistent estimators for the for sigma squared, for this unknown quantity sigma squared. So therefore, we have some approximation, some guess for the variance of x and bar. So therefore, we have some guess of, so when I put a hat on something, that means we are estimating this thing. So this is an estimator for this unknown quantity. So the variance of x and bar is unknown because sigma squared is unknown, but sigma squared can be consistently estimated. So that suggests we can estimate the variance of x and bar as well. You can use the following estimators, or this one. We can use either of these as an estimator for the variance of x and bar. And this can be computed from the data, and therefore you can compute this number from the data and see how big it is. In particular, in practice, we actually don't use this variance estimator all that much. We use the square root of these estimators. And the square roots have a name called standard error. A standard error of the estimator is an estimator for its standard deviation. It's an estimator for the square root of its variance. So the standard error of an estimator is an estimator for square root of its variance. And in this case, if you use sigma hat squared to estimate the sigma squared parameter, then the square root of this is a standard error. If you use xx squared to estimate sigma squared, then square root of this is the standard error. So it is denoted by s dot e, x and bar can be sigma hat divided by root n, or sx divided by root n. Either of these two serves the purpose of being an estimator for the standard deviation of the variance. Of course, they don't give you the same answer, but in large samples, when n is large, they are not very different. So the story is that either will do. In large sample, they are very similar. They're in general very similar. In small sample, there is the convention of using this one instead. So in small samples, so conventionally, we use sx divided by root n for some reason. But the reason is that sx squared is an unbiased estimator of sigma squared. But that doesn't mean that Sx is an unbiased estimator of sigma. So that doesn't mean that this is an unbiased estimator of sigma squared divided of the square root of this. Even though we don't have unbiasedness, we still just conventionally use this as the standard error in small samples. In large samples, it doesn't matter which one you use. They would be very similar anyway. Now, variance is only one aspect of the random variable x and bar. It would be nice to know the whole distribution of x and bar. If we can figure out the whole distribution of x and bar, then we will be able to calculate all kinds of probabilities, the probability of how x and bar is different from mu. The probability, for example, we can calculate the probability that x and bar minus mu being greater than 1, for example, if we know the whole distribution of x and bar. Now let's start with the case where the underlying distribution, F is the distribution, the population distribution, is the distribution from which our IID sample is drawn. So if that distribution is normal, if that is a normal mu sigma squared distribution, then what's going to be the distribution of x and bar? So let's start with this case. Well, we're going to use a very important property of normal distributions of independent normal random variables. We learned at the end of the video for normal distributions that the sum of independent normal random variables are also normal. Or maybe I should say a sum of independent normal random variables is normal. So that's more grammatically correct. So a sum of independent normal random variables is normal. That is a very important property that independent normal random variables have. Their sum remains normal. So therefore, if we have an IID sample from this normal distribution, then the sample average will be a constant times the sum. So the sum is going to be normally distributed. Constant times the sum is also normally distributed. That's another property of normal random variables. Linear transformations of normal random variables are still normal random variables. And multiplying by a constant, that is a linear transformation. So the sum is normal, and therefore 1 over n times the sum is also normal. That means the sample average is a normal random variable. And the sample average is normal. But what are going to be the parameters for the normal distribution? We already know the parameters for the normal distribution, because for the normal distribution, the first parameter is the expectation. We know the expectation of sample average equals the population expectation. And we know the variance of sample average equals sigma squared divided by n, equals the variance of the population expectation, a population distribution divided by n. So therefore, the sample average, the distribution of the sample average follows directly from this property of normality and from the expectation and variance for x and bar that we have already calculated. So the distribution of x and bar is normal mu sigma squared divided by n. So when the sample is normal, the sample average is also normal. That is probably not very surprising. What is surprising, however, is that X in bar, we're going to show that the sample average is going to be approximately normal. It's going to be close to normally distributed. Maybe not exactly, but approximately normal, even when the underlying population distribution is not normal, as long as the sample size is large. So what I'm saying is, if the underlying population expectation is normal, then X and bar is exactly normally distributed. The more striking thing is that even when the underlying population distribution is not normal, sample average is still going to be approximately normal, as long as the sample size is large. And that is guaranteed by the central limit theorem. And before going into the central limit theorem, we want to make it more rigorous of what we mean by approximately normal, approximately some distribution. So what does that mean? Approximately distributed as something as long as sample size is large. So the precise sense in which this approximation works is convergence in distribution. So that's the precise sense in which the approximation works. So what is the definition of convergence in distribution? Let's consider a sequence of random variables. So this is Zn, where n runs from 1, 2, 3 to infinity. This sequence is a sequence of random variables. This is a sequence of random variables. Notice that I use n to as the subscript, not I, because I don't want you to confuse this with the sample. So this is not a sample from some underlying distribution. This is just a sequence of random variables. So this is a sequence of random variables. And let Z without the subscript be a continuous random variable. So a continuous random variable. We say that the sequence Zn converges to Z, converges to this continuous random variable Z in distribution. I should add in distribution. We say that Zn converges to Z in distribution as n approaches infinity if for any little z in the real line, on the real line, we have the probability that Zn less than or equal to little z converges to probability that z less than or equal to little z as n goes to infinity. In other words, the CDF of Zn converges to the CDF of z as n goes to infinity. So convergence in distribution to continuous random variable is defined as the convergence of the CDF at every point. So just to give you an example of a sequence that does converge in distribution. So let's Zn be a normal distribution, Zn be normally distributed, Zn be normal, 0, n plus 1 over n. So n plus 1 over n is the variance of Zn. And let Z be standard normal. I claim that Zn converges in distribution to Z. How do you show that? It's easy to show. So probability of Zn being less than or equal to Z equals probability that this constant, which is the square root of the inverse of its variance. This constant times Zn less than or equal to this constant times little z. So what happened? I just multiplied this constant to each side of this inequality. And this constant is a positive constant, therefore that multiplication doesn't change this inequality. So this event and that event are exactly the same event. So therefore that they have the same probability. The reason I want to do that is I want to have a random variable here that is standard normal distributed. So Zn is normal 0 n plus 1 over n. Therefore, this constant times Zn is also a normal random variable. And the expectation of that random variable is 0, because the expectation of that equals the constant times the expectation of Zn, which is 0. So that expectation is 0. Expectation of this constant times Zn is constant times expectation of Zn, which is 0. And the variance of that constant times Zn equals square of that constant times the variance of Zn, which is 1, because variance of Zn is the inverse of this constant. So therefore, this random variable is standard normal distributed. So that implies this is standard normal distributed. If that is standard normal distributed, and this is a constant, this probability equals the CDF of normal evaluated at this value. CDF of standard normal evaluated at this value. The CDF of standard normal is a continuous CDF because standard normal is a continuous distribution. So that function is a continuous function. So if the argument converges to something, then the CDF of the argument converges to CDF of that limit. Well, it is very clear what that converges to. So that converges to Z, because n over n plus 1 converges to 1. That converges to Z, therefore the CDF, which is continuous, CDF of that converges to the CDF, standard normal CDF of Z. And that is exactly probability that Z less than or equal to little z. So we have proven that for any given little z value, the CDF of Zn converges to the CDF of Z. Therefore, Zn converges to Z. So Zn converges in distribution to Z. So we use the notation, this notation, arrow sub D, to denote convergence in distribution. So Zn arrow sub D Z is read as Zn converges in distribution to Z, or Zn converges to Z in distribution. So that's what convergence in distribution means. Once we have convergence in distribution, we can now introduce the central limit theorem. So the central limit theorem, which is also written as CLT, which is also abbreviated as CLT. For the central limit theorem, the setup is kind of similar to the law of large number, the weak law of large number. We're going to have an IID sequence of random variables. This xi, I runs from 1 to n, is a sample, is an IID sample of size n from some distribution f. And when the sample size increases, we promise that the added xi's will also be follow the same distribution as the xi before them, and the added xi's will be independent from the xi's before them as well. So when we consider this, so that's what we mean by considering this as a sequence of IID random variables. They are IID random variables. Each xi has the same distribution. So E of xi equals mu. Variance of xi equals sigma squared. Assume that sigma squared is finite. Now, given this IID sequence with these properties, the CLT says that this transformation of the sample average converges in distribution to a standard normal random variable. So it converges in distribution to Z, where Z follows a standard normal distribution. You can also directly write this. You can also directly write this without going through a limiting random variable. You can directly write this transformed xn bar converges in distribution to standard normal. So both are correct ways of stating the result. So this is, if you pause for a moment, you see this is an incredible result, because all we're saying is that xi is a sequence of IID random variables with some mean and some variance. We say nothing about what these random variables are, how they are distributed. They can be binary, they can be uniform, they can be Poisson random variables. They can be many different kinds of random variables. They can be drawn from many kinds of distributions. And those distributions could be very different from standard normal. But averaging over a large number of independent, identically distributed random variables from those distributions does the magic of turning the average into a standard normal random variable. So averaging produces normality. So that is the essence of central limit theorem. So averaging produces normality. The sample average of IID random variables from any distribution with a finite variance will behave like a normal random variable as the sample size grows to infinity. So you might be kind of wondering, why don't we just use x and bar converges to in distribution to something? Why do we have this root n, this minus mu, this sigma? The idea is simple. If you don't use this, if you don't do anything, if you don't do the scaling and the recentering, x and bar the expectation of X bar is stable, constant. Expectation of it is mu. It doesn't change with the sample size, which is good. But the variance of X bar changes with the sample size. So, and the variance of X bar goes to 0. So if you don't scale it by root n and recenter by mu, X bar, we know it converges in probability to mu, and that is a constant. That is not a distribution that is very useful for calculating the probability of events regarding X bar. So the reason for that root n is to stabilize the variance of X bar. So if you subtract off the mean and multiply it by the variance, then the variance of this scaled version of the random variable is n times the variance of X bar, and that is sigma squared. And that is stable for any n. So in the limit, you are bound to find a random variable that has a stable variance, that has a variance sigma squared. Because the variance of this is sigma squared for any n, the limit, the limiting distribution of that is bound to have a variance that's sigma squared instead of 0. Okay, so that's why we scale it by square root n. Square root n is used to stabilize the variance of the sequence. But why do we scale it by the inverse of the standard deviation? That is actually not necessary. If you don't standardize it by the sigma, the standard deviation, what you are going to get is if you don't do that, this still converges in distribution to something interesting, and that's going to be normal 0 sigma squared. And that is an interesting distribution using which you can calculate probabilities of certain events regarding X bar. We scale it by the inverse of sigma just so that we have a limiting distribution that's that doesn't depend on any parameter that whose CDF we can the CDF we can look up from a table. Okay, so scaling by square root n is super important. Scaling by this inverse of sigma is not very important. Whether you scale it by the sigma or not will give you doesn't affect the ability that the sequence converges in distribution to an interesting random variable. It only affects which random variable it converges in distribution to. All right, so that is the central limit theorem. And before doing some examples regarding using the central limit theorem, I want to show you some Monte Carlo simulation to see the power of central limit theorem. So in the Monte Carlo simulation, I'm going to draw samples from a uniform 0-1 distribution. A uniform 0-1 distribution has a we know the uniform 0-1 distribution is supported on 0 and 1. And it's a flat line on that interval. So that is the probability density function of the uniform 0-1 distribution. So that is the fx little x. This distribution, in many ways, it is different from the standard normal distribution or any normal distribution. It is very different from the normal distribution. Normal distribution is single peaked. single peaked, and it has support on the whole real line. It looks like a bell shape. That is very different from the uniform distribution. However, when you draw a large sample of from the standard norm or from the uniform distribution and take the average of your sample, the average is going to behave like a normal random variable. And if you scale it properly, it's going to behave like a standard normal random variable. So let's do an Excel Monte Carlo simulation and see the central limit theorem in action for the uniform random variable. Now let's try to illustrate the central limit theorem using Monte Carlo simulations. So what we are going to do is to generate 1,000 independent copies of a random sample. And the random sample size will range from n equals 1 to n equals 5 to n equals 20. And at each sample size, I will generate 1,000 independent copies of the sample and calculate the sample mean with the square root n scaling and the mu recentering with the right recentering and the right scaling. So, and then I will calculate the CDF of this random variable using these 1,000 independent observations of this random variable. And I will compare that CDF with the standard normal CDF and see how quickly they get close to each other as I increase the sample size. Okay, now let's get started. I'm going to first generate the 1,000 samples. Let's start with n equals 1. With n equals 1, I will just, to generate the sample, I will put each sample on a row and I will generate 1,000 rows. So for n equals 1, let's open data analysis and choose random number generator. And I will generate a sample of size 1. I will generate 1,000 samples. And the sample is generated from uniform 0 to 1 distribution. And I will start the data set at this D2 cell. I want to leave the first 3 columns empty because I want to put this sample mean, the scaled and recentered sample mean on the first column and the 2 CDFs on the next 2 columns. So I will start the data set from D2. So I put D2 here. Okay, now I have generated the 1,000 samples. Each sample is of size 1. So now with the sample already generated, I can calculate this quantity, this random variable, which is square root n times the sample average minus the population mean, and then divided by the population expectation. For uniform distribution on the interval 0 to 1, the population expectation is the midpoint of the interval, which is 0.5. And the standard deviation is the square root of 1 over 12. Now let's calculate this quantity, which should be square root of n, and it's 1 in this case, so square root 1 times average of this row. This row only contains this 1 column, so just average D2 minus 0.5, which is the population expectation, divided by standard deviation, which is square root of 1 over 12. So So this is this random variable's realization corresponding to the first sample. So I'm going to try to calculate, copy this formula to the next 999 cells. And so I will have this random variable calculated for each of these 1,000 samples. So what I do is to drag this bolt cross all the way down to the last row where we have data. So now this is 1,000. This column contains 1,000 realizations of this random variable. And using this 1,000 sample, okay, of this random variable, so this is a random sample, an IID sample of 1,000 of this random variable. Using this sample of 1,000, I can calculate the CDF of this random variable. So what is the CDF? The CDF is the probability that this random variable is less than or equal to some given value. At what given value do we want to calculate this CDF? I'm going to calculate the CDF at each and every point in the sample. In order to calculate the CDF for each point, I'm going to just use the frequency that this random variable is less than or equal to this value in this sample of 1,000. To calculate the frequency, I use the Excel function sum and combined with if, that will, so these two combined will count the number of points in these 1,000 points that are less than or equal to any given value. Okay, so count if A2 to A 1,001. I count whether these are less than or equal to this value in the cell A2. And if this condition is true, I will give the value, give this function, if function, the value 1. And if the condition is false, I'll give the if function value 0. When you sum up this if function of this 1,000 dimensional 1,000 by 1 vector, you get a count for all the cases that have value less than or equal to this A2 value. And now that's the number of occurrence. I will divide that by 1,000, which is the total number of points in this sample. And I get 0.937. And that is an estimate for the CDF of this random variable at this point, 1.549. So that is the CDF estimate. And I can fill up all the cells in this column for this 1,000 points. Just simply by double-clicking on this bold black arrow. So I have gotten the CDF of this random variable. Now I want to calculate the CDF of the standard normal distribution at the same points. So this column will be filled with the standard normal CDF at these points. So the standard normal CDF can be calculated using the function norm.dist, norm distribution. The point of evaluation is this point, and I want standard normal, so I want the mean of the normal distribution to be 0 and the standard deviation to be 1. And the fourth argument of the function is a logical value is either 1 or 0. If you write 1, then this function calculates the cumulative distribution function for you. And that is what we want. So I will put 1 here. So now that gives you the CDF of the standard normal distribution at this point. I'll double click this bold black cross to fill all the cells below it. So this column contains the standard normal CDF. This column contains an estimate of the CDF of this random variable. When n equals 1, this random variable, basically, it is a uniform random variable centered around 0 because we recentered by the mean. So this CDF should be the CDF of a uniform distribution, which is linear. And this CDF is the CDF of the standard normal distribution. When n equals 1, these two, we can expect them to be very different. How do we compare them? Let's try to compare them using a plot. So what I'm going to do first before doing the plot is to sort the data. So I'm going to click on this triangle to select the whole table. I'm going to sort the data according to the value of this random variable, according to the first column. That will allow me to draw a nice plot of the CDF against the value of this random variable. So I will sort, click sort here, which remember is under data. So we clicked on data in the middle, you can see sort. I want to sort and I want to tell the sort dialog that my data has headers. Header means the first row that doesn't contain any number, but it's the title of the columns. So my data does have headers. So my data has headers. And then I want to sort according to the value of this random variable. So I want to sort according to column A with this header. So sort by column with this header. Sort on cell values, order smaller to largest. So I will do that. And the data now is sorted according to the first column. It's important that you select the whole table to sort, because otherwise this column will be out of sync with the other columns and the values in them will change. All right, so now I have sorted the data. I'm going to select the first 3 columns because this is the data that I want to use to plot. I want to plot the CDF and the standard normal CDF. I choose insert, and then I choose this scatter plot. I want it to be lines, so it's easy to read. Smooth lines. And I get this. So that is the chart that I get for n equals 1. So the blue curve is the CDF, is an estimate of the CDF of this random variable. Sometimes we call this kind of estimate using the sample frequency to estimate the population CDF. That sample frequency, we sometimes call that the empirical CDF. Empirical CDF is an estimate of the CDF of this random variable. And that is depicted by this blue line. As you can see, it's quite linear. And that's in line with our expectation because we know this random variable is uniform. It is a uniform distribution with a shift. And we know that's still a uniform distribution. A uniform distribution has flat PDF. And when you integrate a flat PDF, you get a linear CDF. So the CDF of this random variable is flat, is a linear, it's a straight line. And the CDF of standard normal is, we know it's not a straight line. Standard normal has support from -infinity to +infinity. It cannot be a straight line on all of these. So it's flatter on the tails and more steep in the middle. So it's this orange curve, and it's quite different from uniform from this uniform CDF. So when n equals 1, distribution of this random variable is not very close to standard normal. Now let's consider n equals 5. So here I have already generated the data because generating 1,000 independent samples takes some time, so I've already generated the data. So these columns contain the data, 1,000 independent samples. Each sample has 5 observations. So each sample has size 5. And for each of the sample, I'm able to calculate the value of this random variable, which is the square root n times the average of the sample minus the population expectation divided by the standard deviation of the population distribution. And that's the value that you get for the first sample. And by copying this formula to all the other rows in this column, I can calculate this value, the value of this random variable corresponding to each of the random samples, each of the IID samples. So this is a sample of 1,000, so 1,000 independent draws from this random variable, from the distribution of this random variable. I can calculate its empirical CDF using the same method as we used for the n equals 1 case. And I can calculate the standard normal CDF corresponding to these values as well. I can do that for each of the values, each of the 1,000 values. Now I can draw, now I can try to draw a plot of the CDF and the standard normal CDFs. To do that, you would want to sort the data according to the first column. This data is actually already sorted, but let's do it again just for illustration. I'm going to sort according to the first column, but also recognize that the first column, all the columns have headers, have titles. So I sort by the column with this header, and we'll sort on the value of the cells and order from small to large. So this is already sorted. Now I'm free to plot the CDFs. So I will plot using the smoothed lines. Actually, I made a mistake by not selecting the relevant columns to use for the plot. The relevant columns are the first columns, the first 3 columns. The first column is the value, the little x value that we put on the horizontal axis. And the second and the third columns are the 2 curves appear on the y curve, on the vertical axis. So this B and C are the 2 curves shown on the graph, on the plot. So I would have this plot. And you can already see that the CDF of this random variable, which is the left-hand side in the equation in the central limit theorem, the CDF of that random variable is already quite close to the standard normal CDF. So the blue curve is the CDF of this random variable, while the orange curve is the standard normal CDF. There is some slight difference in the middle of the distribution, but in the tails, they are very close. Now that's with the sample size n equals 5. That's not even very big. Now let's increase the sample size even more and see whether the CDF gets even closer. It actually does. So this sheet has the data with n equals 20. So the data is from column D to column W. So it's these 20 columns of data. Each rho is one random sample of size 20, and there are 1,000 random samples. Now, for each sample, we can calculate this recentered, rescaled sample average, which is square root sample size, square root 20 times the sample average minus 0.5 population mean divided by the standard deviation of the population. I do that for all of these 1,000 different samples. I get 1,000 IID draws of this random variable. And I can calculate the empirical CDF using these 1,000 draws evaluated at each of the points in the 1,000 draws. The CDFs can be calculated the same way as we did for n equals 1 case. And this column stands for the CDF, or also called the empirical CDF of this random variable. And column C is the CDF corresponding to each of these values for the standard normal distribution. Now, with the data has already been sorted, so I will not sort it again. Sorted according to the first column. So I will just insert the graph, the smooth scattered plot. And that is the graph. As you can see now, the two CDFs are even more close. The discrepancy even in the middle is now much smaller comparing to the n equals 5 case. So in the n equals 20 case, the two CDFs are already very close. So now we have illustrated that CLT does work, at least for the uniform distribution case. So at home, you can try other distributions. You can change this data into samples from other distributions. You can use your data analysis, random number generation, and choose your desired sample size, desired number of samples, and desired distribution. You can choose from these different distributions, and that then you can verify that when n increases, when n grows very large, the CDF of this recentered and scaled sample mean does get close to the standard normal CDF. You might need a different n, a smaller or bigger n, when the distribution you draw your data from is different. For uniform, it looks like n equals 20 is already very good. For other distributions, you might need a bigger n. So that is an illustration of the central limit theorem. And we are going to talk about the application of the central limit theorem in the next video.